So go with the new folder, give the name, right click on it, open in terminal, give the command csh to initialize the tool, source space /home /install /cshrc virtuoso ampersand. The tool will be initialized. This is the main window of virtuoso, which should not be closed at any point of time. Go to file, go to new library, create library. You can give any name. While giving the name, don't give the space. You can use underscore. Choose the third option, attached to an existing technology library. Say OK. So here what we are doing is we are attaching some library whose transistor will be using. So if we use GPDK 180, then we will be using MOSFETs of 180 nanometer length. Say OK. So the library has successfully attached to the technology library GPDK 180. Next, go to file, new, cell view. So just choose your library which you have created and give the name, cell name. So let us do inverter. Here you can press I or go with this option, create instance. So choose GPDK 180 because from that library we will be using the MOSFETs. You can change the parameters here, like we have width and width. So generally it is done for beta ratio analysis. So this was NMOS. Again press I, go with PMOS, hide it. You can place the PMOS above the NMOS as per the design and press escape. So you are in any mode, say if you are in delete mode, you have to press escape. So it comes into normal mode. Then press P or go to create pin. Here you can give the pin names. So we are taking 3 pins as inputs. The main input is A. VDD and ground also acts like the pins, input pin. So A, VDD and ground. The pins comes in the same order as we had given the names. You can choose output pin also by once again pressing P, and you can place it on the right hand side. Then you can choose the narrow wire, create narrow wire, or you can press W and do the connections, drain to drain short. Both the sources of PMOS and NMOS are going to sources, voltage sources, that is NMOS source to ground and PMOS source to VDD. Gate to gate short and input is shorted to that gate. Then output is shorted from the drain. This is the body of the MOSFET which is connected to the voltage source. NMOS body goes to the ground. So you can press F. You can scroll in and out so that your circuit zooms in or zooms out. So if you are lost somewhere, you can press simply F, so the design fits on the screen. Now the design is ready, you can check and save it. So if there are any warnings or errors, the same will be displayed here, which can be debugged. And next we'll go to create in cell view from cell view. So here what we are doing is we are creating the symbol of that inverter. So no change here, simply say OK. Here we will place the pins in the direction which we need. So VDD we need at the top, therefore I'll cut paste it. Ground I need at the bottom, so I'll just cut paste it. Ctrl X, Ctrl V. So left side A, right side Y. This is the symbol. You can delete the unnecessary thing here. So press delete, just click on the boundary and the yellow color text, and this can be renamed. Just right click, select it, right click, right click and edit it. So you can give any name. So I given INV, which indicates the inverter. Again check and save it. So whenever you complete any design, you have to compulsory check and save. This is our schematic and that was our symbol. Both can be closed. Next, go to file, go to new cell view, because using that symbol, what we will do, we will test the circuit which we have designed. So you can give the name test as new cell view, and you can import your symbol by pressing I. Go to your library and there you will find your inverter symbol. So that you can choose and place it here. Press I, go to your analog lib library. From there you can take few standard parameters like ground. So take the ground, place it at the bottom. Again press I, go to analog lib. You can take VDC, and here you click somewhere here so that the parameters, DC parameters or DC voltage, whatever you need, that you can type it and hide. So you can press R for rotating it. I am rotating it in such a way that positive is coming towards VDD. Next, again press I. You can type V pulse and again click somewhere here so that all the parameters are displayed. So here you can choose the voltage 1.8 volts, which we had chosen for the same VDC. Choose the same voltage. You can give the period, rise time, fall time and all. So fall time I am taking 1 nano. Don't give the units here, just write 1 n. Rise time, fall time I have taken same 1 nano. And pulse width I have taken 10 nano. Period I have taken 20 nano. Actually period is double of pulse width generally. So seconds it is taking automatically. You can give delay but not required. So this is our V pulse, which we will give at the input side, because we will give 0 and 1. By taking that 0 and 1, the inverter will give us the output. You can press P for output. Give the same name which is present here. We had taken Y, so I am taking again the Y. Place it on the right hand side, and if you need, you can take VDD also. So go to analog lib. You can take VDD also. And you can place it here. It is not required actually. Without VDD also you get the output. And if you need, you can take one capacitor also. Capacitor, you can choose 1 pico or 1 femto. Anything is fine. Escape. Take the wire and do the connections. All the negatives are going to the ground, and this is the input which is going to A. Ground is shorted to ground. This is our output, and this also goes to ground. So you can simply check and save. No, we don't have any errors. If you want to confirm it, you can go to main window where you can see schematic check completed with no errors. So my library name followed by cell name schematic has been saved. So for that you have to press Windows button. When you press Windows button, you can see all the windows which are opened. Next, what we have to do is go to launch ADEL. We will run the simulation here. So here you go to setup, model libraries. Check that 180nm model spectre gpdk.scs is attached. Usually it will be attached. Just confirm it. Then go to analysis, choose transient. Transient analysis means it is input and output waveforms will be plotting. Stop time you can decide upon the period. So 2 or 3 times of period you can take the stop time. So we had taken 20 nano, so I have taken here 40 nano. Choose the moderate accuracy and say OK. Then again you can choose DC analysis also. We can plot DC analysis. In DC analysis, save the DC operating point. That we will get the operating point of the circuit and choose the component parameter. That component parameter means it is the input with respect to which we will be changing the or will be varying the input and plotting the output. So press Windows, come here. Here we have chosen the input and the parameter is DC. We will start the simulation at 0 volts and we will stop the simulation at 1.8 volts. And the sweep type, let it be automatic, not an issue. Say OK. Again press Windows button, come to our ADEL window. Here we need to plot the output, input and output. So go to outputs, to be plotted, select on design. So I will design the wire, input wire and the output wire. Just verify both of them have appeared here and the plot should be ticked. Then what you can do is you can go to outputs, save all. So this step will help us to get the power consumption, which is additional. And next you can simply run the waveform. So you can split the strip. You can change the color and style. You can change the style and even you can change the thickness also. Here also the same thing. As per so width I'll take it thick. So yeah, this is our input which is 0 volts here, and the output it is changing, it is reaching 1.8 volts. There is a little delay here due to the capacitor which we have placed. Okay, if you can change that value of capacitor, we will get the exact waveform. So because the capacitor charges and discharges, right, we get these kind of waveforms. You can simulate it without capacitor, then you will get exactly these kind of waveform. Like there will not be any delay. So input versus output, when input is 0, output is 1, and when input is 1, output is 0. Coming to the DC characteristics. In DC characteristics, the straight line, it is nothing but the input which is changing from 0 to 1.8. And when the input is 0, the P MOSFET is on, therefore we are getting the output as 1, because P MOSFET is called as pull-up device which pulls up the output, means the output is held high. And as the input approaches higher value, that is when it goes near 1.8, at that time P MOSFET will become off and N MOSFET will become on, therefore there is switch in this output. So output from high, it is going down to 0. And this is our actually the intersection point, that is 756 millivolts. So this is the you can say operating point. Okay, and we can change the width of the MOSFET. So here what you have to do, press escape you can click on this symbol, right click, go to Descent Edit option, open it in new tab, and you will go to your basic design, select any MOSFET which you want to change, press Q or go to right click and properties. So here if you change the width, so I'll do it 4 micro, and what we can do, actually what I'm doing, I'm changing the W by L of PMOS. So W by L of PMOS and W by L of NMOS ratio has been changed now. What I'll do, I'll just close it. You can note this point, it is 756 millivolts, the intersection point. Now I'll close it, and to get the clear waveform, what I'll do, I will delete this part, escape, and now I will rerun it. Sorry, I need to save it first. So here also I need to check and save, here also I need to check and save, and then I need to rerun it. So now as you can see, the waveforms are very clear. Style, I'll take it solid, and if you want to see only this waveform, then you can simply click on this card button. So as this is our input, as the input goes from high to low, the output is changing from low to high. So this is the inverter, right? Again, if you want to get back to the same window, so here also you can change the style and even the color and width also. Now you can see the intersection point has been changed. It is 828 millivolts. Earlier it was 756 millivolts. That means this entire this output waveform, which is falling from high to low, it has been shifted to the right hand side. Why it has been shifted to the right hand side? Because we have made PMOS more stronger. If you remember, I had changed that width of PMOS from 2 micro to 4 micro. So because I have made width of the PMOS, I have increased, it will carry more current, therefore the output will stay at the logic 1 for a longer time. So this is the study of beta ratio and simulation of inverter. Next what we will do, we will go to tools, we can go to calculator, and here what we will do, we will try to calculate the delay. So just go to the delay option here, and when you go to delay option, just untick the clip, select the wave, and you need to take 2 signals because delay can be taken between 2 signals, input and output. So for signal 1, what you can do, just click on VT here, just see the cursor, and in VT what you have to do is select the input wire, and this is the stack, Control X and Control V. So just place whatever has come in the stack to the signal 1. Same for signal 2, go to VT, select the output wire, and this you can place it Control X and Control V. Okay, and here we need to change the threshold value. Actually threshold value should be always 50% of the maximum value, that is voltage which we have given. So I have made it 0.9 because the actual voltage we had given 1.8. And here you can take edge type 1 rising and edge type 2 falling, and simply say apply and OK. When you do apply and OK, you will get an equation for delay which is automatically generated. Okay, and you can go with this option, evaluate the buffer and display the results in a table. So you will get some value, that is 10.65 picoseconds. This is the value for input is rising. See here, input is rising and the output is falling here. So this is TP. One we have TP LH and one we have TP HL. We have to take the average of both to get the delay. So here what I do, instead of rising, I'll just change it to falling, and where I have falling, I'll just change it to rising, so that I get both TP LH and HL. What is LH and HL? High to low and low to high. Okay. Now re-evaluate. So you get one more reading, that is 95 picofarads. So 10.65 plus 95.89 pico. Just add both of them and take the average and divide by 2. So roughly it comes around 10 plus 95, 105, 106. 106 divided by 2, it comes around 53 picoseconds. So your delay is 53 picoseconds. Okay. And the same delay, even it can be calculated from this waveform also. Here what you need to do is you need to mark the horizontal lines and vertical lines, and you can zoom in to calculate the delay. Okay, with respect to input, how much is the delay, or how output is varying with respect to time. And for power calculation, what we can do is, in the waveform window, just go to browser and just double click on TRAN, and here you get the PWR option, that is power. Even click on it and right click, just choose the option new sub window. So when you choose this new sub window, the power reading, the power will be plotted here. I will just show you here. This is the power. Okay, and this you can send it to calculator and take the average. So here or you can simply type it, average, and evaluate the buffer and display. So it is consuming 7.03 microwatts.